In this video, we are going to cover section 2.7 on inverse functions. The definition of an inverse. A one-to-one function f has an inverse function g if f composed with g of x equals x and g composed with f of x equals x for all x in the domain of both g and f. Inverse notation means how we are going to write an inverse and indicate that it is such. So the function g is the inverse of the function f using the definition above, and when we write it, we're going to use inverse notation that looks like this. F with this little -1 up here kind of looks like an exponent. However, that's not what it means. When you attach a little -1 up high on a function as opposed to a number or a variable, we read that as f inverse. It has nothing to do with meaning the power -1. So anytime we see f with this little -1, that's denoting that f inverse is what we're talking about. All right, also part of what happens in the definition of an inverse, the domain of f is equal to the range of f inverse and vice versa, because essentially what's happening is you're reversing the roles of x and y. In the function f, the x's, when you change those to be the y values and you change the y's to be the x values, you have the inverse function. All right, so when we are asked to verify inverses or to decide if two functions are inverses, we use the definition, which is composition of functions. So f of x equals 3x plus 8 and g of x equals x minus 8 over 3. We're looking to verify that these are inverses or decide whether or not they are based on the definition. So we're going to find f composed with g of x, meaning f of g, so the function g becomes the input for f. So that means you're going to replace all the x's of the f function with the expression for g, x minus 8 over 3. So here is f, so it's 3 times x, so this expression, x minus 8 over 3, becomes the x plus the 8. And then you're going to simplify. So 3 multiplied by this quantity means the 3 on the top out here will cancel the bottom, leaving x minus 8 plus 8. Then the 8's cancel each other out and we're left with x. That's what we're hoping happens. If that doesn't happen, then they're not inverse functions. It should also happen in reverse. G composed with f of x would mean g of f of x. So the f of x function now becomes the input in the function g. So we're going to replace all the x's of g with this expression 3x plus 8. So here's g, so this x gets replaced with 3x plus 8. Then we subtract 8 according to what g says and then divide by 3. So this time we clean up the top first. These 8's cancel out, leaving 3x on the top. Divided by 3, then the 3's cancel, and again we get x. When that happens in both directions, then we know that the two functions are inverses of each other. If we're only given one function and we're asked to find the inverse, here are our 4 steps. Step 1, replace f of x with y because that's what f of x represents. Then we're going to interchange x and y because essentially that's what's happening when you create an inverse. You're reversing the roles of the two variables. After we've interchanged them, we're going to solve the new equation for y. And once we have y by itself, then that represents the inverse function, so we're going to replace it with inverse notation. So we're going to do 2 examples. Our first example, f of x equals x minus 1 cubed. So step 1 says replace f of x with y. So we're going to write y equals x minus 1 cubed. Second step, interchange x and y. So the y becomes an x and the x becomes a y. Everything else stays the same. Now we have to solve for y. So since y is inside of this quantity, we want to get rid of the power of 3. So to get rid of the third power, we take the cubed root. So the cubed root of this side will cancel the 3 and leave the y minus 1, but then I have to cube root the other side. And now we just add the 1 to both sides. So we get the cube root of x plus 1 equal to y. Once we have y by itself, we call it f inverse. So the y becomes f inverse of x, and then that would just equal whatever I ended up with, x cubed plus 1. Our second example is a little bit harder because of the algebra, but it follows the same 4 steps. F of x equals 2x minus 3 divided by x plus 1. Step 1, replace f of x with y. Gets me to here. Second step, interchange x and y, so the y becomes an x. Both of these x's have to become y's, everything else stays the same. And now I have to solve for y, but I have y in 2 different places, so that's why this is a little bit harder, but we can still get through the steps. So our first step would be to clear the fraction. So if I multiply both sides by this y plus 1, it cancels it on the right, leaving just the top part. And on the other side, I just multiply the x by that quantity, y plus 1. So my fractions are now gone. Next step is on the left, we're going to distribute x. So y times x plus x times 1, so I get yx plus x. The right side does not change. And remember, I'm trying to solve for y, so I have a y term right here and I have a y term right here. So I have to put those 2 terms on the same side of the equation. So I'm going to leave the yx over here and I'm going to subtract 2y over here. But at the same time, this term doesn't have a y, so I'm going to subtract the x to the other side. So all I did to get from here to here is subtracted 2y from both sides and subtracted x from both sides. So they kind of switch places. Next we can factor out y, leaving x minus 2. This side does not change. And now I can divide by x minus 2 on both sides. So I have this minus x minus 3, and I'm dividing it by the x minus 2. And over here that would just cancel and leave me with just y. So once I have y by itself, we call that f inverse of x. In the definition of an inverse, we said that the function had to be 1-to-1 in order to have an inverse. So the term or the phrase 1-to-1 simply means that it must pass the horizontal line test. The horizontal line test works just like the vertical line test. If you can draw a horizontal line that touches the graph more than once, then it's not 1-to-1. So here's an example of both kinds. So in this graph, any horizontal line that I draw across here will only touch the graph 1 time, no matter where that horizontal line is. So that would mean this function is 1-to-1, which means it has an inverse. However, a similar curve that's just slightly different in shape that looks like this, here if I drew a horizontal line, I could find one that touches the graph more than 1 time, meaning this is not a 1-to-1 function, which would also mean this does not have an inverse. So it must be 1-to-1 for the inverse to exist. Next, we're going to go over the graphs of inverse functions and how they are related. Anytime you have 2 functions that are inverses, the graphs of f of x and f inverse of x are reflections across the line y equals x. So for example, here's the line y equals x. It's a diagonal line through the origin with a slope of 1. All right, so here are an example of 2 functions that are inverses. So let's say f of x looks like this right here. That would mean f inverse should be its reflection. So what happens when you're creating the reflection across that line, if we looked at just the given function f of x and wrote down the ordered pairs, this point right here is the ordered pair 0, -1. This point right here is the point 1, 0. And then the other point we've labeled here is the point 2, 1. So if I make a table just based on the ordered pairs for f, my table for f inverse should just be reversing the roles of x and y, so switching these around. So this point, 0, -1, would turn into -1, 0. The point 1, 0 would turn into the point 0, 1, and the point 2, 1 would turn into the point 1, 2. And then if I plot these new points from this new table, I should have my inverse graph. So notice -1, 0 would be here, 0, 1 would be here, and then 1, 2 would be here. So I would draw in my graph, and then we can see that they are reflections across that line. So we're going to try two examples of, if we're given a function f, can we graph its inverse using that procedure? So here the graph in blue is given as f. So we're going to start by writing down the ordered pairs on this given graph. So -3, 0, -1, 2, and then this point here is at 5, 3. So to create my inverse function graph, I just switch these around. So this becomes 0, -3, this one becomes 2, -1, and this one would switch around to be 3, 5. So these points should plot to form the inverse. So 0, -3 is down here, 2, -1 would be right here, and then 3, 5 would be up here. So here we connected a straight line between the first two and then another line between the second two. I'm going to do the same thing here. Connect a straight line here, and then connect a straight line from here to here. And we can see then, if we draw in that diagonal, that they are reflections across that line. Let's try a second example. Again, the blue graph is given. The ordered pairs I have here are -2, 4, -1, 2, and 0, 1. So I'm going to write those down in a table. My new table is created by switching the roles. So this becomes 4, -2, 2, -1, and 1, 0 when I switch them around. When I plot those points, I get 4, -2, 2, -1 is here, 1, 0, and then I can draw in my graph to show that it is a reflection across this line. I just put the dotted line in there so we can see it. All right, and then our last example, we're just going to kind of tie it all together. Find an inverse, graph them, and then give the domain and range of both, which should be reversed. So here we're given f of x equals x squared minus 2, and we're told x greater than or equal to 0. So we're given a one-part piecewise function. If they didn't restrict our domain on this, this would not be 1-to-1 because it would be a parabola. So this is a parabola, x squared shape that moves down 2, but we're only graphing it for x's that are 0 and larger. So my vertex of x squared would have started right here at the origin. I would have shifted it down 2. But if I'm only graphing for x's that are greater than 0, it's just the right half. So this would be my graph of f of x. All right, so then we're going to find the inverse. Y, change f of x to y, we get x squared, y equals x squared minus 2. Interchange x and y, so x equals y squared minus 2. Solve for y, so we add the 2 to the other side, x plus 2 equals y squared. Then we square root both sides, so when we square root here, we just get y. When we square root here, we get the square root of x plus 2. Normally we would have a plus or a minus sign, but we don't need that because we're told we're using positive values for our variable. And then that is our inverse. Y would be f inverse, and we would end up with this equation. So if I'm graphing f inverse, that's the square root shape, moved left 2. So if I shift it from the origin left 2 and then draw my square root graph, I get this graph. And then notice that the domain and range happen to just be reverse of each other. So if I'm looking for the domain of f, we were given that. They gave us the domain, 0 to infinity. And then if I look at my graph, the range of f is -2 to infinity, because it goes up from the y value -2. For f inverse, the domain, that was this graph, started at -2 and went forward, so -2 to infinity. Notice that's also the range right here. And then the range of f inverse, the y value here is 0 and it goes up, so 0 to infinity, which happened to be the domain of f. Notice domain becomes the range, and the range here becomes the domain. So that is the end of section 2.7.